Okay, so the point of this video is to touch on something that it's not particularly hard, but we didn't really do it last year, so I want to make sure that we end up talking about it. And it's something that has to do with gravitational potential energy that can save you a lot of work in certain cases. So, for an example, let's imagine that you have a 7-kilogram cat that sits on a tree branch, and that tree branch is 4 meters off the ground. We want to know the cat's gravitational potential energy with respect to the ground, with respect to a lower branch that is 2.5 meters off the ground, and C with respect to a branch that it's currently on. So let me draw a very crude picture here. So we've got a cat on a tree branch. Here's another tree branch. Here's the trees. And we have our cat here. There we go. Okay, so this branch right here is 4 meters off the ground. This branch here is 2.5 meters off the ground. The ground is obviously down here. So there's 1.5 meters between these two branches. So I guess I'll just label that. We got 2.5 meters here, 1.5 meters here. So the whole thing is 4 if you take it from the position where the cat is. When it asks for the cat's gravitational potential energy with respect to the ground, what that means is if you set the ground to be where h equals 0. Because remember, when we talked about potential energy in the 2 videos ago, I said that you can actually make h equals 0 wherever you want it to be. Now, and as long as you're consistent with that throughout the problem, it shouldn't make a difference. Now, some of you might be saying, well, wait, how can you say that something that's not the ground is the ground? That's where 0 is, okay? Remember, all we're doing is we're just setting an origin point. We're setting our coordinate axes. That's really all we're doing. If we say that the cat, if we want to know the cat's gravitational potential energy with respect to the ground, that means set the ground to be h equals 0. So if this is 0, then the cat is up 4 meters. And it's very easy to calculate the cat's initial gravitational potential energy here. That would be mg h naught. Mass of the cat is 7 kilograms. Acceleration due to gravity is 10 meters per second squared. And h naught is 4. 7 times 10 times 4 is 280. So the initial gravitational potential energy of the cat is 280 joules. Let's actually skip down to A. As the cat safely jumps to the ground, what is the change in the cat's gravitational potential energy, again, with respect to the ground, so keeping that h equals 0 at the ground? Well, we're looking for the change in gravitational potential energy, which is the final gravitational potential energy minus the initial. That will end up being mgh minus the initial gravitational potential energy of 280 from this situation where we're saying h equals 0 at the ground. Well, if it's at the ground and h equals 0 at the ground, then h is 0, and this whole thing becomes negative 280 joules. In other words, the change in gravitational potential energy was negative 280. 0 minus 280 is negative 280. Let's try it for B. What about the gravitational potential energy of the cat initially with respect to a lower branch that is 2.5 meters off the ground? So again, what this means is if lower branch is h equals 0 meters. Well, in that case, the initial gravitational potential energy, same equation, okay? Cat still has the same mass, that's not affected. Acceleration due to gravity is exactly the same, still 10 meters per second squared. What's the height now? If this is h equals 0, how high above that is the cat? It's 1.5 meters above that. So, in this case, we've set our h equals 0 line to be here. The cat's 1.5 meters above that, so that's obviously going to change our initial gravitational potential energy. 7 times 10 times 1.5, our initial gravitational potential energy is 105 joules. So you might say, well, wait a sec, that's a huge difference. Okay? Well, it depends what we're going to do with that number. Let's see the change in gravitational potential energy when the cat jumps to the ground. So again, this is going to be mgh minus, this time it's going to be minus 105 joules. M is 7 kilograms, G 10 meters per second squared. What is the final height? Well, if this is h equals 0, if we set that up here and we're using that in this calculation, then we have to keep h equals 0 here. So if this is 0 and that's 1.5, what does this level have to be down at the ground? That has to be negative 2.5. Because it's 2.5 meters below below the h equals 0 line. And interestingly, if I do 7 times 10 times negative 2.5, I get negative 175 joules minus an additional 105 joules. Look at that. I get that the change in gravitational potential energy is still negative 280 joules. Interesting that even though I set h equals 0 at a different spot, the change in gravitational potential energy is the same. Let's see if it works for the last one. What about if we want to know the gravitational potential energy with respect to the branch it's currently on? That means if the 4 meter branch, this branch, I shouldn't say 4 meters, I don't want to confuse you with the numbers. If this branch is h equals 0 meters, that means if this is h equals 0 right here. Well, that's kind of easy, because if that branch is h equals 0, then the cat's at 0, and therefore the cat has no initial gravitational potential energy. Very different answer than we got before. Again, let's try to find the change in gravitational potential energy as the cat jumps down. Let's see, so that's 0. So we're just looking for mgh. Mass of the cat is 7 kilograms. Acceleration due to gravity is 10 meters per second squared. H, well, if this was 0, then down here has to be negative 4. Because if we're measuring height, when you're measuring height, you're kind of always assuming up is positive. So going down should be negative. This branch is 4 meters above the ground, or this is 4 meters below the branch, and if this is 0, that's got to be at negative 4. And 7 times 10 times negative 4 is negative 280 joules. So interestingly, even though the individual gravitational potential energies at each point were different, the change in gravitational potential energy was the same. That wasn't affected by our choice of h equals 0. Now, you might be saying, why did we go through all this? Well, at the end, we're asked, what is the speed of the cat just before it hits the ground? We could pick any of these situations that we want. When we go through our conservation of energy equation, it doesn't matter. Let's allow for a couple different things. Let's allow for maybe there's some initial kinetic energy. Maybe we're going to pick a situation where there's some initial gravitational potential energy. There's definitely going to be some final kinetic energy. And let's allow for a situation where there's possibly some final gravitational potential energy. Well, okay, so in reality, we know that the cat is motionless. It's just sitting on the tree first. So this is going to be 0. If we want to know the speed of the cat right before it hits the ground, then we can rearrange this equation to k equals ug minus ug naught. By bringing the k, let's see here. Oh crap, did I do something wrong? Oh, okay, no, I'm fine. K equals Okay, so that would be a negative. Okay, sorry. Lost my train of thought for a second. So we see that bringing the k to the other side gives us negative k equals ug minus ug naught. But look at this. No matter what we said for our ug naught, no matter what h equals 0 line we chose, we always got the same thing. So it doesn't matter where you set h equals 0. Where would it be easiest to set it? Probably somewhere where one of these cancels out. So that's either the first option or the second option. I'm actually going to pick, let's say, I'm going to pick the most obvious one. Let's say that we should make the final gravitational potential energy 0. Okay? That would be like making h equals 0 down here. So that would be, let's see here. taking off this one. That means we're left with negative k equals negative ug naught. And if you were confused about why you had negative k, well, see, now that negative is going to go away. And we get that the final kinetic energy is going to be equal to the initial gravitational potential energy, which means k equals 280 joules. And since k is equal to 1/2 mv squared, that means 280 joules equals 1/2 7 kilograms v squared. And we simply solve for v. With v being 8.94 meters per second. Now, we would have gotten the exact same thing no matter if we had chosen the set of numbers for h equals 0 at the lower branch or h equals 0 at the upper branch. Okay? So, what this is all going to show you is that depending on where h equals 0 meters is, UG will change. But it's not UG that ends up ultimately mattering. It's the difference in gravitational potential energy which allows you to determine how much the final kinetic energy is. But UG, delta UG, will always be the same and is the relevant term. So the moral of the story is that you should set h equals 0 meters somewhere convenient. And what that means is set it somewhere that it makes it so that the calculations are easier for you. So convenient really means that a term will cancel out for you. Okay, if you set it somewhere convenient, you won't have to calculate the gravitational potential energy at 2 different spots. Hopefully you'll only have to calculate it at 1 spot. That would be why, in my opinion, the process used in A or the process used in C are better, because in each of those we have set the gravitational potential energy to be 0 either where the cat starts or where it ends up, and those are the 2 points that we really care about. Setting it as 0 in the middle is, you can do that, but that is not very useful to you, okay? Because you're not canceling anything out, you're not eliminating any work for yourself. So what this has all been is just to show you that you can set h equals 0 wherever you want, and you will be able to solve the problem the same way in any case. If you have any questions on this, you can come see me. Hopefully this makes it a little bit easier for you to solve some problems. I'll see you later.